This one. If I stand here and talk like this, is that clear? Okay, terrific. So why this topic now? Because it turned out to be more interesting than I thought it would be. Spoiler, there are no grand, spectacular meteor showers expected in the next year. So this is about people being fiendishly clever at using naked eye observation to find really important insights about the Earth's situation in space. I used to collect fruit crate labels. Anyway, so the idea of meteor originated in ancient times. So here is from an ancient manuscript, the world as it was thought to be structured at the time. And at the very bottom is the Earth with water, earth, air, and then the topmost layer of Earth was fire. And above fire, you're in the realm of the planets, the sun, the moon, and the stars, the lifeless, deathless, unchanging heavens. So the fire was the top layer of the part of the universe where things could change. And originally, a meteor referred to anything, any changing phenomenon in the layer of fire. Later, so that's how weather got to be called meteorology, changing things in the atmosphere. Later, the word meteor was restricted to what we would call shooting stars. So if we are sky watchers, we are familiar with this list of some of the well-known meteor showers, the ones that produce the most meteors every year, especially the Perseid shower in August and the Leonid shower in November in some years. And those two showers will be big in our story tonight. So I'll start with the modern view of meteors and then go back to how it was figured out. On any clear, dark night, when we're looking at the sky, if we wait long enough, in addition to the stars that aren't moving, we'll see occasionally a little flashing streak, a shooting star, officially called a meteor. And on average, if there's no meteor shower going on, you see one of those maybe every 10 minutes or so. And their directions are completely random, so they're called sporadic meteors. On some nights, we see extra meteors, and they all seem to be coming from the same part of the sky, and we say we're having a meteor shower. The place from which the meteors in a shower seem to be coming is called the radiant of the shower. And meteor showers are usually named after the constellation in which the radiant appears. So the Perseid meteor shower has a radiant in the constellation Perseus, the Leonid shower in Leo, and so on. The apex of Earth's motion. So suppose I am the Earth, and here is the sun, and I revolve around the sun. The direction I'm going is here. And when I look toward the direction that I'm traveling, that point in the sky is the apex of the Earth's motion. And if meteors were caused by particles that were just completely random in space and moving completely randomly or not moving at all, then as I went around, I would see on average shooting stars radiating from the apex of the Earth's motion. In a little while, we'll meet Giovanni Schiaparelli. He called this the meteoric sun, which would exist if the particles that cause meteors were completely random. Zenithal hourly rate. So this is a measure of how many meteors you're going to see. It means the number of meteors that would appear to an ideal observer if the radiant of the shower were directly overhead at the zenith. So a big zenithal hourly rate is over 60, like the Perseids on a good night can be 120. And then if you want to get academic, a meteor is the flash of light in the sky. A meteoroid is the particle in space before it hits the Earth. If some object comes in from space and survives the trip through the atmosphere and lands on the ground, then that object is a meteorite. We now know in modern times that meteor showers are caused by particles left behind by comets as they revolve around the sun. And as the Earth revolves around the sun on the same date every year, it will pass through the same region of its orbit. And if there is a trail of comet particles there, we will get a meteor shower every year. The Earth travels about 67,000 miles an hour in its orbit. And meteor particles that are in orbit around the sun, if their orbit goes way, 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 way out into the solar system and then comes back in and passes near the sun at about the same distance as the Earth, their speed will be about 94,000 miles an hour. And so if those particles are coming at us, we can have a head-on collision with speeds above 100,000 miles an hour. Here is a picture that is supposed to show at the bottom the sun, and then up here we have the Earth, and the arrow shows how it rotates every 24 hours as it revolves around the sun from your right to your left. And then the little dots are supposed to be meteoroids in space. So if the meteoroids in space are not doing anything special, if they're not coordinated, then you would expect to see more meteors in your sky in the morning hours of nighttime, because then the Earth's rotation turns you so that you are facing into the oncoming stream of particles as you plow through them. And you would see fewer meteors in the evening part of the nighttime because that is the trailing side of the Earth. Another important thing about this diagram is remember the apex of the Earth's orbit. Suppose here's the sun, I'm the Earth, here's the apex. As the Earth revolves around the sun, the apex will sweep through different constellations. So if this will become very important later because people realize if the radiant of a meteor shower moves, that's an indication that the Earth actually does revolve around the sun. So if I'm doing this, I might start out in March, some month, with the apex pointing at the constellation Leo, for example. And then 3 months later, the apex is pointing toward, say, Ophiuchus. And 3 months after that, some other constellation. If the particles, the meteoroids, are moving in a coordinated way so that there's a meteor shower with a radiant in some other part of the sky, the same principle applies. As I go around the sun, the relationship is changing, so I will see the radiant in a different direction from Earth's point of view as the Earth revolves around the sun, if the Earth actually does revolve around the sun. That's what this slide was all about. So as I go around, the apex will point in a new direction every day. On your left, a railroad track, the rails are parallel. We know they are, but as they go off into the distance, they appear to join at a point on the horizon. Artists call it the vanishing point. In the same way, the particles in a meteor shower are traveling in parallel paths, but they seem to come from a point in the distance in the sky. That's the radiant, and a meteor shower is usually named after the constellation that the radiant is in when it's most intense. Then, if the particles are moving, things can get more complicated. So in this little picture, imagine that we are flying above a car that's driving through a snowstorm. So the car, let's say, is going 30 miles an hour and we're flying along with it. And there's a snowflake up there. Well, if there's no wind, as we drive along, we're going to see the snowflake go by our car, just like this, from front to back at 30 miles an hour. And so as we look out the window of the car, and I've actually seen this, remember when we used to have blizzards? I've noticed this, and maybe you have too. If you're driving right into a heavy snowstorm with heavy, big snowflakes, you see a radiant of snowflakes in front of the windshield of your car. But suppose there is wind blowing from your right at 30 miles an hour. Then that is going to change the relative motion of you and the snowflake so that the snowflake is going to be going sideways while you approach it, and you'll see the radiant of the snowflakes move over to the right side of the windshield. And I can remember seeing that driving through blizzards as the wind is howling and changing direction. You can see the radiant of the snowflakes moving back and forth across the windshield. So this was the surprise to me. This summer, I was scheduled to appear on a podcast that a friend of mine does. I will plug it. It's a podcast called This Week in Space. My old friend Rod Pyle is the host, along with Tarek Malik, who is the editor-in-chief of space.com. And they do usually current events in space travel and also future things like plans for building colonies on Mars and things like that. And I was going to be on this summer to talk about the summer sky and the Perseid meteor shower. So I thought I would read up a little bit about the Perseid meteor shower. I thought I knew pretty much about it. And I thought it must have been known for many, many, many centuries. It's one of those obvious things in the sky. You know, when I worked at the planetarium, kids would sometimes ask, who discovered Jupiter? Well, it's a really obvious thing in the sky. It's not so much that you discover it, is that you notice that it's there and give it a name. And I thought meteor showers were like that as well. But no, it's surprisingly recently that meteor showers are figured out. At least I was surprised. So I'm going to sort this out. There are many pieces to the story, and I can't claim to have read all of them, but I'm going to sort it out. I'm going to sort it into a German thread, a French-Belgian thread, an American thread, and an Italian thread. And we're going to go back to the 1800s because that's when the work really started of figuring it out. Before then, very little evidence of any interest in meteor showers. So questions were, they didn't know at that time, are meteors phenomena in the atmosphere like rain and lightning? Or are they caused by particles from space? And if they are particles from space, do they come from our solar system or from beyond the realm of the sun? None of this was known. So we're going to start with the German thread. And the German word for shooting star is Sternschnuppen. And when I discovered that, the first thing I heard in my mind was Terry Garr saying it, as in Young Frankenstein. She just died this week, so there was a particularly appropriate time to remember her. So back in the late 1700s, these two young student astronomers, they were either students or had just graduated, Heinrich Wilhelm Brandes and Johann Friedrich Benzenberg in Göttingen, had this idea that if you had two people some distance apart and they observed the same meteor and measured the angle at which it appeared to them in the sky, they could use math and trigonometry to figure out how high in the sky a meteor really is, because nobody knew. And so they observed from two separate points a few kilometers apart. And this was hard to do. This is the principle. You have your two observers, you know the distance between them, they record the angle at which they see the same meteor, you put it together with trigonometry, and you can figure how high the meteor is. Now, it turns out being only a few kilometers apart is not far enough to get a good measurement, because they will be measuring almost the same angles. They didn't realize how high meteors really were. They were able to tell that meteors were higher than a lot of people thought, tens of kilometers, and they were able to get a rough estimate of the speed of meteors. But it was really difficult. Here's one of the reasons I think it took so long to figure out meteor showers: the awesome, terrible power of sleep. And so one of them says, it was particularly disadvantageous for our observations that we had to make them and even record them completely alone. And for the subsequent ones too, it was inevitable that the walk to our observation points, combined with the uncomfortable position in which we had to spend the night, often on bare ground or at most on some straw, should not have exhausted the body and robbed the mind of some of the cheerfulness so necessary for observation. But they were able to conclude a few things. Meteors were fast, speeds up to maybe 58 kilometers per second relative to the Earth. Now that's interesting because the speed of the Earth going around the sun is about 30 kilometers per second. So these things are hitting us faster than we're traveling around the sun. That indicates that these must be particles that we're colliding, they're coming at us and we're colliding with them head on. So they're not just randomly floating particles. The other thing they realized, and this is what I love about this topic, is these people realized with these naked eye observations, you could discover really important things about the Earth. We are able to cite two phenomena as direct demonstrations of the motion of the Earth in space. Galileo said that the Earth moves, but he didn't prove that it moves. For him, it just made more sense that the Earth moved. There was no physical proof that the Earth moved until 100 years before this, when an astronomer named Bradley measured what's called the aberration of starlight, which means that if there's a star way up here, and if the Earth is moving, to see that star, you have to tip your telescope a little bit forward to catch the photons. It's like walking forward into a rainstorm, tipping your umbrella in front of you. Very hard measurement to make. Bradley had made it back in the 1760s. And at that time, that was the only physical evidence that the Earth actually moves. And these kids realized meteors could be another piece of evidence that the Earth moves in space. One is the aberration of light. The other, which we still need to establish by more exact observation, is the apparent motion of the shooting stars. Since this phenomena is known through few observations and deduced by me from them, we cannot give it much weight as yet, but I do not doubt that future observations will confirm it. They realized that just observing meteor showers could provide proof that the Earth moves. Okay, now the Belgian-French thread. In French, they're called étoiles filantes. Francois Arago was a leading French astronomer in the 1800s, and he was famous for directing people to topics that would be good to work on. And he had heard about the very intense Leonid meteor shower that was seen in America in 1833. And that, as I'll show, kind of kicked off the interest in meteors. And he contacted his friend, the Belgian mathematician Adolphe Quetelet. Quetelet's specialty was statistics, particularly social statistics, like using numbers to analyze what masses of people do, what does the average person do, and so on. And so Quetelet said, you should analyze meteors and tell us if there's anything there. So Quetelet actually recruited some observers, sent them out to watch meteors and count them on different dates, and published his results in 1836. He concluded that on average, one observer on an unexceptional night will see about 8 meteors per hour. But he noticed meteors are more frequent around November 8th to 15th and around August 8th to 15th. Those are what we now call, there we go. Those are what we now call the dates of the Orion, Leonid and Perseid meteor showers. And he kept compiling this data and published a list of other dates of the year when extra meteors were seen. So this is like the first published list of annual meteor showers. So this is what, 1837. And he made a graph. So this is a wheel with a spoke for each month of the year. And this shape shows how many meteors are seen on average in each of those months. And you see a big bulge for August and a pretty big bulge for November. Another observer of meteor trends, an astronomer I'm sure you've never heard of, Remy Armand Cuvier-Gravier, was an industrialist and amateur meteorologist, and he hoped meteors would provide clues to the weather, and he did observing for many years. I think he had helpers as well, analyzed the frequency of meteors by time and date, and found more of the trends that we're going to see that I'll tell you about in a minute. Schiaparelli, whom we will get to in a minute, quoted Cuvier-Gravier's data a lot. So now the American thread, switching to English, shooting stars. The big thing in the history of American study of meteors was the Leonid meteor shower in 1833. This started, it was the night of November 17th, I think, or the morning of the 18th, started 2 or 3 in the morning, and all over the eastern United States, people said there were thousands per second, more than anyone could count, lit up the sky. This picture is famous. It turns out it was made decades later for an evangelical religious book to illustrate the concept of the Day of Judgment and the Second Coming. But it's a great illustration of the idea. So these pictures that do a good job to go viral. So there were newspaper reports from all over the eastern United States of this fabulous phenomenon that was seen in the sky, the 1833 Leonid shower. So a Yale mathematics professor, Denison Olmsted, got interested in this, put a note in the newspaper and said, would you please send me your reports of what you saw on this meteor shower? He got reports from all over the eastern United States, and a couple of important things came out of it. People noticed that there was a radiant in this meteor shower. All the meteors seemed to be emanating from a point in the sky that was in the constellation Leo. And it stayed in the constellation Leo all through the night. This was a clue that the meteors come from outside the atmosphere, because if meteors were an atmospheric phenomenon like rain, they wouldn't favor any particular group of stars. But the fact that the meteors were radiating from a point that was linked to a constellation, and over the hours of the night, the radiant moved across the sky, was a clue that the meteors were from beyond the Earth. He also reasoned, as I say here, that the fact that there's a radiant at all indicates that the particles are traveling in parallel paths. Remember the railroad tracks. They're parallel, but in the distance, they appear to come to a point. The meteors appear to come to a point in the distance. Therefore, he said, they must be traveling in parallel paths. They're not totally random. This was also a kind of idea that people were ready for in 1833, because the discovery of asteroids had only started a few years before in 1801. So people were getting used to the idea of small things in the solar system. Another Yale professor, Hubert A. Newton, not Isaac Newton, but Hubert Newton, looked back in historical records. He was also got his interest stimulated by the 1833 Leonids, and found back in libraries and other reports enough information to suggest to him that this shower repeated about every 33 years. And he predicted that it would happen again in 1866. Here's an example of the kind of record that he looked at. The German explorer Alexander von Humboldt was in South America in 1799 and saw an intense meteor shower in November in 1799 from South America. And some of the South American people he talked to there, some of the older people, said a similar thing had happened about 30 years before. So Olmsted gathered this kind of evidence to make his case that the November meteors repeat with a heavy shower about every 33 years. Another American, Edward C. Herrick, there's an article about him in Sky and Telescope back in 1996. And he was interested in the Perseid meteor shower, which, as we now call it, the Perseid meteor shower, which happens in August. He saw the November 1833 shower. And then one night in August of 1837, he was walking home from his job at the bookstore and saw extra meteors, and went back and looked through the records, because he was a bookworm, and found records of meteors around August 9th in many previous years. So he began to recruit volunteers to observe meteors on different nights and see if he could find out more about the dates of meteor showers. So, pulling all his evidence together, he concluded that the August shower is near its peak for about 3 days and weaker for about 2 weeks, and that it has a radiant in the constellation Perseus. And the August shower is usually heavier than the November shower, except in the really big years, for the November showers about every 33 years. And he also found evidence for what we now call the Lyrids and the Geminid meteor showers by looking back through old records. Another idea that was floating around at this time was the idea that some people believe that every meteor must be part of a shower, Therefore, every meteor must have a radiant that it's coming from. And so people who believed this would analyze meteor records and look for radiants until they found them. And they inferred that there were some radiants that did not move. Remember, I said if you're going around the Earth and the apex is this way, as the months go by, the radiant of a shower is going to, or as the days go by, the radiant of a shower is actually going to move slightly through its constellation. There were some people who concluded that there must be some meteor showers where the radiants don't move, stationary radiants. And so by this statistical self-deception, there were a list of thousands of radiants by the end of the 1800s, and these were just red herrings. It was a total waste of time. Another American, Edwin F. Sawyer, an amateur meteor observer in the evenings, but only until midnight, the awesome, terrible power of sleep, wrote regularly for the magazine of the Boston Scientific Society, maybe sort of like the Rochester Academy of Science in its day. And he recruited volunteers and taught them how to observe meteors and record their directions carefully on a star chart. And he wanted to discover new radiants. He also put out lists of stationary radiants to look for and see if they really existed. So he published lists of radiants of meteor showers, and here's one of them. There was an article about who should get credit for discovering the Perseid meteor shower. And another person that should be named, perhaps, is this man in Cincinnati, John Locke. He was the head of a girls' school, and his hobby was observing the sky. He noticed that there was a meteor shower every year in early August and wrote about, and that it had a radiant in Perseus. And he wrote about it to a local newspaper. So does that count as a scientific announcement for which you get credit? Some people would say yes, some people would say no. Were there some people who had known about the Perseid shower all along? I think it was, I don't remember who it was that brought this up, but somebody noticed and had discovered there was a tradition in the Catholic parts of Germany that every year around August 10th, if you looked in the sky, you would see the tears of St. Lawrence coming down from the sky. St. Lawrence was one of the founders of the Christian church. He was martyred on August 10th in the year 258, so his feast day is celebrated on August 10th. And the way the Romans did it to him was to put him on a gridiron and roast him over a fire. And the story goes that as the flames were curling around him, after a while, he said, "I'm done on this side, you can turn me over." And for his ability to make such a smart-mouthed wisecrack at such a time, he's now known as the patron saint of comedians. Anyway, so there may have been a knowledge at a certain level of the Perseid meteor shower going back many centuries, and astronomers just weren't aware of it. Okay. We're going to go on with, I'm going to make sure I have my information here because it's not advancing.
Who needs that?
Yeah, let's try that. There we go. Thank you. Okay, now we're getting to the end. Stelle cadenti, falling stars, the Italian thread. And we're going to, this really revolves around a long and very nice relationship between these two Italian astronomers. Giovanni Schiaparelli, who is most famous for observing the planet Mars and making sketches with linear features that he called canali, and that kicked off the whole idea that Mars might be inhabited. That all happened much later in his life. So most of the pictures of Schiaparelli that we see show him 15, 20 years later. He did his meteor work when he was in his early to mid-20s. A good friend of his was Father Angelo Secchi, Now, Schiaparelli was stationed at the observatory in Brera, which is part of a district of Milan, Italy, in northern Italy. Secchi was at the observatory in Rome. And Secchi is most known for early attempts to classify stars by their spectra. But Secchi was one of those people, he was just brilliant. He would shake brilliant ideas out of his sleeve. For example, he was the inventor of the Secchi disk used in oceanography, a white and black disk that you, at midday, lower into the ocean on a rope and keep letting it down until you can't see it anymore. And the depth is a measure of the turbidity of the water. This was just a casual toss-off idea for him. This is the level at which he worked. Anyway, Schiaparelli being slightly younger, Secchi really liked him. They had a very nice correspondence over 16 years. So here's the debate as it was going on at that time. Oh, I should say one other thing. When they started communicating in 1861, Italy had just been unified for the first time under one king. Before that, Schiaparelli's observatory was in the Lombardy kingdom and Secchi was in the Papal States. And so both of them were anxious about who they were going to be working for after Italy was unified under one king. So the debate about meteors, there were two camps, the atmospheric hypothesis people and the cosmic hypothesis people. The atmospheric people said temperature, humidity, and so on, those things vary with the time of night and the season of the year. Why shouldn't meteors also have their own variation? They're just another atmospheric phenomenon like weather. And they didn't pay attention to radiance because they were interested in looking at the meteor broadside to see what it looks like and see if they could deduce anything from the light. And it was said that they refused to even look at the radiant because the radiant would be a piece of evidence that the particles come from outer space. The cosmic people said the variations by time and season can be explained in terms of Earth's motion, Earth's rotation and revolution around the sun. And the fact that meteor showers have radiance indicate that these particles are in their own orbits around the sun. And the fact that the radiant of a particular shower actually moves slightly over the course of a few weeks is evidence that the Earth is revolving around the sun. Secchi, at first, was more he leaned toward the atmospheric camp because he was interested in Earth physics and weather. But he did repeat the Brandes-Benzenberg idea of having two observers far apart look at the same meteor and try to measure its altitude, only he did it better with the observers farther apart. He edited a meteorological bulletin, but nonetheless published articles by Schiaparelli arguing for the cosmic hypothesis. He and Schiaparelli both observed the 1866 Perseid shower. And he, as I said, he was interested in using the height of the meteors, but this is brilliant. He said, if you measure the height of a bunch of meteors, and if you find a maximum height beyond which you don't see any more meteors, that could be a clue as to how high the top of the Earth's atmosphere is. What a brilliant insight. And this is the kind of thing the kind of idea he would come up with in his spare time. So what the data indicated about around this time, especially the data from Cuvier-Gravier, Cuvier-Gravier is the data that Schiaparelli uses the most, that outside of the major meteor showers, forget about those, average meteors are more common in the fall than in the spring. They're more common in the morning than in the evening. And the most common direction for meteors is east to west. And all of those things would be explained better if you assume that the meteors are caused by particles from space and you have a rotating, revolving Earth plowing through the cloud of particles to make the meteors that we see. So Schiaparelli wrote several papers about this in the form of letters to Secchi. And one of them is this 110-page book that was translated into English, fortunately, back in 1943, beautifully organized. This is like a 25-year-old guy, and he sums up in 110 pages everything that was known about meteors at that time and argues his view that, as I'll show you, meteor showers are caused by particles from comets. So this diagram here is from one of his books, and he goes through this long argument. Suppose that the particles that cause meteors are completely random in space, then analyze how many you would see at different times of night, at different seasons of the year. Just naked eye observations with enough statistics could even reveal the average speed of meteor particles in their orbits around the sun. So a complicated geometrical argument there. He found from this analysis that the average speed of a meteoroid in its orbit around the sun, not relative to the Earth, but in its orbit around the sun, the average speed of one of these particles is about 140% of the speed of the Earth in its orbit. That is a magic number. 140% of the Earth's speed would be the speed of a comet in a highly elliptical or parabolic orbit crossing through Earth's neighborhood. This is a lesson from Isaac Newton's physics. And he has a wisecrack in there that he had used Cuvier-Gravier's data to prove the opposite of the hypothesis that Cuvier-Gravier was supporting. Anyway, here's the physics that Schiaparelli knew. Over on your right, you have, that could be the sun or any other massive object that has things orbiting around it. So you could be in a circular orbit. And if you were at a circular orbit at a certain distance from, say, the sun, then you will be going at a certain speed that you can figure out with equations from a physics textbook. If you are going a little faster, you might be in an elliptical orbit, an egg-shaped orbit. And if the far end of that orbit is way far out here, that's called an eccentric ellipse. And if the far end of that eccentric ellipse goes way, way, way out to infinity, then you are in an orbit called a parabola. And the other thing that the Newtonian physics textbook will tell you is that if you're in a parabolic orbit, your speed, where that blue arrow is, will be the square root of 2 times your speed if you're in a circular orbit. The square root of 2 is about 140%. And Schiaparelli said, what things do we know in the solar system that travel in these orbits that are very long ellipses or parabolas? Comets. So he saw the resemblance between the particles that make meteor showers and the known orbits of comets. He also got into this. Over on your right, that's an illustration by Etienne Trouvelot of a meteor shower, and you see them making these crazy turns, and I guess some people thought they saw that. I would say that's a result of rapid eye movements while you're watching a meteor. It just doesn't happen. But people believe they saw it, so Schiaparelli has to put in a few paragraphs offering explanations for why a meteor could make one of these bizarre turns. And he talks about things like non-spherical projectiles and spinning projectiles from rifled cannon barrels. He's got a chapter about boomerangs, and maybe something like that's going on, and that's why we see these weirdos. But they're only 0.3% of all the meteors, so don't worry about it too much. Anyway, he puts it all together. From a completely incomplete theory of the said phenomenon, I had the audacity, or rather the temerity, to conclude that the average absolute velocity of the shooting stars should not deviate much from the parabolic velocity, and that the orbits of the meteors should therefore be very elongated conical sections like those traversed by comets. He also used some of his knowledge of physics to analyze what would happen if you had a cloud of small particles and they passed in their orbit very close to the sun. And he shows that the little particle would eventually be spread out into a long stream that might eventually extend all the way around the orbit. I was pleasantly surprised to find that a cloud of rare material, whether continuous or discontinuous, when moving about the sun, according to the law of gravity, is necessarily transformed into a long, thin stream. And if that stream goes all the way around the orbit, then Earth may pass through it every year as Earth revolves around the sun. And that might be what's going on with the Perseid meteor shower. If the stream does not go all the way around, then there will be times when the stream is just not there when the Earth goes by and you get nothing special. That would be like the Leonid shower, which is great every 33 years and kind of blah in between. So he concluded that meteor showers come from comets. The orbit of the periodic meteors of August, calculated according to the new theory, was found identical with that of the great comet that appeared in the summer of 1862, Tuttle's comet, or as we call it, Swift-Tuttle. The tens of thousands of meteors that made the nights of August 9th, 10th, and 11th so splendid and interesting form the escort of that noble heavenly body and occupy the entire ellipse of 100 years which it describes in space. The shooting stars certainly have originated with the comets or from the comets. However, the awesome, terrible power of sleep is still there. We are very far from knowing all the radiance. The catalog of the radiance of the Northern Hemisphere is itself almost entirely based upon observations in the evening, since observations in the morning hours have not been made diligently because of the awesome, terrible power of sleep. And more, another insight from naked eye observations and pencil and paper analysis, no high-tech fancy schmancy telescopes. And finally, we see what a beneficial function is exercised by our atmosphere as a shield against the masses that the heavens send on us. Without it, we would be continually exposed to frequent blows far more fatal than those of firearms. And here's a picture from back in the 90s from the Mir space station. I think this is the Leonid meteor shower. And here's a picture from more recently. Astronaut Ron Garan took this, and this is a Perseid meteor there entering the Earth's atmosphere. Secchi, I would love to listen to a dinner party with Secchi. He was just great. Science has already made some brilliant conquests in this field. It is enough to mention the discovery of Professor Schiaparelli that these swarms of corpuscles follow the path of the parabolic orbits of comets, so that these are nothing but larger bodies forming part of the same nebulous mass, which, having entered from the depths of space into the sphere of action of the sun, completes its rotation around it in a parabola or in a very elongated ellipse. With this splendid result, the cosmic origin of these bodies and their relation to the aerolites and what are called fire showers has been demonstrated forever. In other words, Schiaparelli sold him on the cosmic interpretation. So another piece to be filled in is, has anybody actually seen a comet turn into meteoroid particles? Schiaparelli looked back to 1618, one of the very first comets ever to be observed with a telescope, and here are some drawings that show what would look to us like a comet breaking up into little pieces. And then there was the famous comet Biela, which was discovered and named by Wilhelm von Biela, and came back as expected a few times, every 6.6 years, and then came back a couple of times, split into two pieces, and then missed a few apparitions. And then on the date that it was expected in 1872, there was a brilliant meteor shower. So it looks like Comet Biela broke up, and then we encountered its pieces in 1872. So comets can break up and produce meteoroid particles. So now we understand, in a basic way, meteor showers, and we understand we've got another piece of physical evidence about how our Earth moves in space and what our physical environment is. That on these dates, we pass through debris left by these objects and see these meteor showers. And there are many others. If you look at the International Meteor Organization website, I think it is, there's over 100 minor small meteor showers that actually have verified radiance. So why did it take so long to figure out meteor showers? I think it was really the 1833 Leonid shower that really kicked off interest in studying meteors. Before then, there wasn't enough astronomy to really have anything to say about them. Another problem was that meteors didn't have a home in the academic structure. the people who studied weather could say, oh, that's a job for the astronomers. And the astronomers could say, oh, meteors, that's a job for people who do weather. We like our jazzy high-tech telescopes. So it was kind of a neglected topic. I love the idea that a major insight about where we are in space came from non-glamorous, low-tech observations, naked eye observations, and counting meteors and mapping where they are and then analyzing it with a pencil and paper. And another thing is the terrible, awesome power of sleep. Photography would have helped those guys if it had been available. If you'd been able to make a camera that could do the watching in the wee hours in the morning for you while you sleep, maybe this could have been figured out a lot faster. So what meteor showers are coming up for us? Well, we expect the Leonids on November 17th, but we are in one of those lull periods between the 33 years. And so zenithal hourly rate of only about 15 is expected, and the moon will be full. And so one of the websites says the Leonids might be better in 2031, 2064, and 2099. So put that on your calendar. As we mentioned before, the Geminids are coming up on December 13th, but the moon is full. The Quadrantids are coming up on January 2nd and may have a very intense zenithal hourly rate, but only for about 6 hours. And if it happens while it's not dark for us, we won't see it. And the moon is practically full for next year's Perseids. So I'm sorry, nothing great to say about spectacular, easy to see meteor showers coming up. Okay, epilogue. Giovanni Schiaparelli was from a educated, well-connected family. His niece, Elsa Schiaparelli, became one of the leading fashion designers starting in the 1930s in the world. Here she is on the cover of Time magazine in 1934 or 35. And on the right, her famous Zodiac jacket, which is in the collection of the Philadelphia Museum of Art, really a beautiful thing. So she built her own fashion house from her ideas. Good for her. Her most famous creation, perhaps, is the lobster dress. The lobster dress was worn by Wallis Simpson for her pre-wedding photographs. This is in the realm of the British royals. Wallis Simpson was the twice-divorced commoner for whom King Edward VIII of England gave up the throne to marry. And people hated her. And somebody said this dress was ideal for making the public hate her even more. It was designed by Elsa Schiaparelli, and she had Salvador Dali paint the lobster on the dress. If you are like me, the first and only time you've ever heard of Wallis Simpson was on the episode of the TV show Seinfeld, in which Mr. Peterman, has a slice of Wallis Simpson and Edward VIII's wedding cake as a collector's item in his office fridge. And one afternoon, Elaine, desperate for a snack, eats it and replaces it with a piece of Entenmann's. So that's, anyway. So Elsa Schiaparelli designed a gown for Zsa Zsa Gabor in the movie Moulin Rouge. She created this perfume called Shocking, and then did more things with, well, this beautiful coat in the center, and then did surrealistic jewelry pieces with Salvador Dali. And the house of Schiaparelli is still very much in business today. Here are Jennifer Lopez, Beyonce, and Lady Gaga all wearing Schiaparelli creations just in the last few years. So the discovery of meteor showers, I found a much more interesting story than I thought it would be. Those guys with beards back in the 1800s were fiendishly clever at using what they had, naked eye observations, to come up with very important insights about where the Earth is in the solar system and what our environment is like. That's what I have. Thank you. Great. Do you have questions? Yes.
Steve, you're familiar with Mile Shine? There's a picture in there, a stereo picture of the.
Okay.
And I just thought you'd be interested. You might want to.
What is the book again?
Sky Shooting
I have seen it, but I don't know that picture. Thank you. I'll come and look at it. Yeah, I can cross my eyes, I think. Mark,
Steve, are there comets that are responsible for more than one meteor shower?
I don't know.
How?
Well, yes, there are two showers attributed to Halley's Comet. Which ones are they? I'd have to, I'm stumped. I don't remember which two they are, but yes. Because it can be complicated now. A comet could shed some stuff. The stuff forms spreads out along an orbit, and then Jupiter comes along, and Schiaparelli knew about this as well, this possibility. Jupiter could nudge the orbit a little bit so that these particles from a particular ejection from the comet are now in their own independent orbit that you might meet at a different time than particles from other ejections from the comet. Yes?
So the peak date for the comments in the early part of your talk were in around the August 8th, August 9th. And now it's like August 11th, August 12th. So it seems to me like that might indicate a precession of the orbit of the comet or of the Earth relative to the comet, or both. You come across anything like that?
I wondered the same thing. And I concluded it must be something like that, but I haven't looked up where an expert says, yes, Jupiter has perturbed the orbit or it has precessed, but it must be something like that. Over a few days, over centuries, it must be something like that. Yes?
So what provoked comet and north cloud that suddenly deviated usual orbit and entered towards the sun?
What I've heard about it is that these things are in places where they're just barely bound, and a passing star, it only takes this, and there's billions of them out there maybe. A passing star at a particular moment may nudge one just enough that it falls away from its original place and heads in toward the sun, and the other 999 million don't. But this is the explanation I've heard, that is that motion of passing stars or any other massive object, they are in such loosely bound orbits that it doesn't take much to change them.
Questions about the line?
Steve, you talked about the different countries. I just heard scientists in different countries that came up with their own understanding. Were they talking to each other? Or were the dates so far off that wouldn't work?
One of the things, first of all, there's not much written about this whole thing. So what I gave you is not a scholarly survey, but what some of the people say is that particularly there was not good communication between America and Europe at that time. So, and the Leonid shower was seen in America, but not in Europe. So the slowdown of communication was a real problem. Yes.
Earlier you talked to, I'm not sure how to say his name, Wettelet or something like that.
Yeah, Ketelé, I was saying.
And he had observers, and they more or less determined our two biggest meteor showers of the year. How many observers did he have?
I don't know the answer to that. Enough to give him some confidence in those conclusions, but that was a real problem all through the 19th century, was, having enough observations. Photography would have helped them.
Anybody else here remember the Leonids that we had out at Ionia? I remember we had a star party at Men Pond Park and invited some of the public out to the site. And knowing that ZHR was something you want to look at, we actually had 4 observers standing around me, all announcing every time we saw a meteor. We were starting to get about 1 per second. Okay, which is 3,600 per hour, and it was getting higher as the dawn was coming up. But we got over 3,000 meteors per hour as an attempt at an actual ZHR. And it bothers me to no end that these ZHR figures get quoted by our local weathermen. Well, you're gonna go see 60 per hour. And ZHR numbers are as if you had view of the whole sky and you adjusted the radiant to be at the zenith. It's not something a person sees. So even though you see a ZHR of, 50 or whatever, it's not real. That's a calculated number. But anyway, anybody else who was there at the meeting?
What year was that? Was that 99?
Yeah.
2001.
So I'm remembering also a heavy shower and an aurora at the same time. Am I hallucinating? In one of those years? No, okay.
I don't think we've ever seen a shower or anything like that again.
Yeah.
Yeah, they were about 1 per second.
And the sky was perfect then. Did that.
I was thinking my car headlights coming in the.
You say it was warm.
Yes, sir. That is a painting of the 1833 Leonid shower done for some publication, and I have no idea whether it represents a real observation or was done because it would sell magazines in the later 1800s or not. Yeah,
It's Canadian.
I think it's supposed to be Niagara Falls, but I could be. Yeah. But it's like today where something goes viral. You look back in the 19th century and there's a few illustrations that you see again and again. And if the publisher couldn't get the original, he'd hire an artist to copy it. So you see different versions of the same picture redrawn.
Different colors.
Yeah.
Some of them are breaking up.
Yeah. The idea here is to sell books.
So next time, then on the last one, he said he saw that and that was the Perseus. That's what Nick Longdale had said.
Yeah, the Aurora and the Perseids at the same time.
Thank you. So it wasn't a Leonid shower. Okay, that makes sense. Nick, do you remember what year that was?
I think it was in the 90s.
I think so too.
So remind us of the size of the typical meteor.
What I've heard is that the particles can be like,
Sand.
yeah, or smaller. Another issue so one of the interesting surveys about this is an article written by a woman at the Rand Corporation as a kind of a hobby project. And she analyzed how well did these astronomers in the 19th century actually know the physics of things like how big the particle would be. And the answer is not very well. In those days, astronomers were not necessarily all up on physics. So Schiaparelli tried to figure out, how much energy would be released as heat and light from a meteor, but he wasn't quite up on all the latest developments in heat transfer as they were known at that time.
And are they known maybe stony or are they icy?
Could be anything, couldn't they? Because if you've got fragments of a comet. So, but a point could be that, so an icy particle could make a meteor. I'm speculating here. The solid stuff from comets is said to be carbonaceous and not metallic. So the meteorites that people usually find on the ground, metallic meteorites, those are fragments of asteroids and they're not generally connected with meteor showers. I bring this up because this is a common thing at planetariums. There's a meteor shower and the next morning somebody will phone in to the planetarium and say, I have this weird rock. Could it have been a meteoroid that fell from the shower? Probably not, because comet particles are they're either icy or this carbonaceous, delicate stuff that will not survive a trip through the atmosphere if it's a small particle. So the metallic things that people find are from other events. Schiaparelli didn't know that though. So he was trying to coordinate the statistics on found fallen meteorites with the appearance of shooting stars in the sky, and that was a wild goose chase. Yes, Brian.
Being it was 2001.
Okay. The big shower that we're all talking about here. Yeah. Yes,
The previous question just made me think, so I'm comfortable thinking of the idea of comet breaking up in the tail, with evidence of that when it spreads out into an orbit. But we have an ion tail and a dust tail, and those are probably spreading slightly different. And, is either one or both contributing to the meteor showers that we see?
David, I think there's a market for a speaker who's an expert on comets to talk about the physical constituents. Yeah,
That's what makes the path so wide that we go through.
Directly out from the sun. It's a different dust tail.
Right. Right.
Mostly with the orbit.
yeah. So I'm not the person to ask about the exact physics of what's known now about how comets break up and produce meteoroid particles, but Schiaparelli figured that there might be some repulsive force in the gas or something like that, but he had no idea. He had no physical evidence at all to go on. I think I'm
Five, that shows maybe meteor showers, I know one was
wrong.
E8, no, you had one that said E8 something, and that's the one until the five branches, and that's like, that is a weird orbit where we only have second, like a small orbit, but what's, oh, okay, daytime.
(2003) EH1, I think it's one of those hard to classify objects. Would you call it an asteroid or an inactive comet?
Yeah, there's something about a rock comet perhaps. That's wrong.
Yeah.
Or meteorite rock.
And there's your two attributable to Halley.
Probably a clear sky on November 18th in Rochester.
It's clear or extremely cold. Other nature does that.
Yeah.
I think it's higher, but the range of 20% or less.
Well, thanks. I feel like I've been up here long enough.